Welcome to the deep dive. We're kicking off a really important part of our CSWIP 3.1 exam prep series today. Our aim is pretty simple, really. We want to help you get ready for that CSWIP 3.1 Welding Inspector Exam. We'll run through some typical multi-choice questions, but, it's not just about ticking the right box. We're going to be digging into the why behind the answers, because actually understanding this stuff, that's what makes you a great inspector, right? Both for the test and out on the job.
That's exactly it, yeah. Being a competent inspector, it's more than just knowing facts off by heart. It's really about having a solid grasp of the metallurgy, the mechanics involved, and what it all means in the real world. So we'll break down each question, connect the dots between the concepts, and give you that context you really need, not just to pass, but hopefully to pass confidently and really thrive in your career.
Okay, great. Let's jump right in then. First question, straight from the kind of thing you'll see. Ready? Which element has the greatest effect on the HAZ hardness of CMN steel? Your options. A, molybdenum, B, chromium, C, titanium, or D, carbon. Have a think. Which one's the main player here?
Okay, for this one, the answer is definitely D, carbon.
Carbon. Right. So for carbon manganese steel, why carbon? What makes it so influential on that HAZ hardness?
Well, carbon is the primary element that controls hardness in steel. Even small amounts make a big difference. Its atoms, they sort of get in the way of movement within the iron structure. That directly boosts strength and hardness. Now, the heat-affected zone, the HAZ, that's the metal right next to the weld that got hot but didn't actually melt. The rapid heating and cooling cycle during welding, especially if you don't manage things like preheat, it can make the carbon in CMN steel form very hard structures, things like martensite. Right there in the HAZ, that potential to form hard structures, that's hardenability.
Okay, so more carbon means a higher chance of getting that hard, maybe brittle martensite in the HAZ. But practically speaking, how much carbon is, too much for these steels? And are there situations where you might actually want that higher hardness, even with the risks?
Good question. That gets into the practical trade-offs. Usually with CMN steels, once you get above, say, 0.25% carbon, the risk of hydrogen cracking in the HAZ really jumps up because of that increased hardenability. So for most structural welds, we're looking for lower carbon or lower carbon equivalents. As for wanting high HAZ hardness, it's rare in the weld itself. Toughness and avoiding cracks are usually the priority for the joint. If you need a really hard surface, that's often done differently, maybe hard facing or surface treatments. We usually see HAZ hardness as something to control, not something to maximize. The main point is carbon's effect is just so dominant in CM steels. Controlling it is key. The other elements listed, motley, chrome, they matter more in higher alloy steels. Titanium does something else entirely, like refining grains.
Right, that makes sense. The huge impact of carbon.
Yeah.
It really sets the stage for thinking about weld flaws. So our next question is about figuring out which defect is the most serious. Which of the following would be classed as the most serious type of defect? Options are A, a buried linear slag inclusion, B, buried lack of inter-run fusion, C, surface breaking lack of sidewall fusion, D, surface porosity. Think about the risk. Which one is the biggest threat?
Out of those options, the most serious has got to be C, surface breaking lack of sidewall fusion.
Surface breaking lack of sidewall fusion. Okay. This really hits on defect severity, doesn't it? Why is that one so much worse than the others? What makes it stand out as critical?
It really highlights a key principle. A surface breaking defect, like lack of sidewall fusion, is bad because it's not just a gap. It's a gap that's open to the outside world, to the atmosphere. That means it's a perfect starting point for a crack, especially if the weld sees any kind of fatigue or repeated stress. And the shape of that defect, that lack of fusion, it's often sharp. That creates a stress concentration, like a tiny notch just waiting to grow. Plus, being open, it can corrode, which just makes everything worse faster.
So it's exposed, and it acts like a weak spot where stress builds up, a real recipe for disaster. How do the other options compare then? Those buried ones, for example.
Yeah, the buried defects, like slag or lack of inter-run fusion, they're internal. Now, they're not good, obviously, they weaken the weld, but they are shielded from the environment. Generally, they aren't as likely to start a crack as quickly as something on the surface, unless they're really big or there are lots of them, and you need specific NDT like RT or UT just to find them, usually. Surface porosity. Well, it's a defect, yes, but it's usually seen as less critical structurally than a sharp lack of fusion, especially if it's within the limits set by the code or standard. Porosity tends to be rounded voids, not sharp stress razors. It really comes down to that crack initiation potential and the exposure.
Got it. That's a really clear distinction. So internal chemistry, external flaws. But what about the welding process itself? This next question looks at a key process control. Inner pass temperature. Exceeding the maximum inner pass temperature specified for a CMN steel weld joint may give. Your choices are A, excessive porosity, B, burn through, C, lower toughness, D, higher strength. What happens if things get too hot between passes?
The correct answer here is C, lower toughness.
Lower toughness. Okay. For anyone maybe not super familiar, what exactly is inner pass temperature? Why is it so vital to control?
Sure, inner pass temperature is simply the temperature of the weld area, the weld metal, and the metal right next to it, just before you lay down the next weld bead, the next pass. And it's hugely important. It basically controls the cooling rate and the whole thermal experience of the weld. If that temperature stays too high between passes, maybe you don't wait long enough for it to cool or it affects the steel's microstructure. Staying hot for too long can make the grains in the steel grow larger, both in the weld metal and in the HAZ. And generally speaking, coarser, larger grains mean worse mechanical properties, specifically lower toughness, the ability to absorb energy without fracturing.
You mentioned grain coarsening. Can you paint a picture of that? What does it mean microscopically, and why do bigger grains make it less tough?
Yeah, think of the steel's structure like a brick wall. Each grain is a brick. The boundary between them is the mortar. Finer grains mean lots of small bricks, lots of mortar lines. These boundaries actually help stop cracks from running straight through. If the grains get coarse, you have fewer bigger bricks. A crack finds it easier to travel a longer distance without being stopped or deflected. That makes the material less able to absorb energy before it breaks. More brittle, essentially. Looking at the other options, excessive porosity, A, is usually more about gas shielding or contamination. Burn through, B, that's often too much heat input on thin material, maybe too slow travel speed, and higher strength D, usually not. Uncontrolled high temperatures tend to degrade properties, not improve them. So yeah, controlling that whole thermal cycle, preheat, inner pass, it's fundamental.
Right. That makes perfect sense. Okay, question 4. This one really digs into welding procedures and following the rules. Changing an essential variable beyond the allowed limits for a qualified welding procedure. The options: A, may change the mechanical properties of the joint. B, may adversely affect the quality of the weld. C, will require a new welding procedure to be approved. D, all of the above. What's the overall impact here?
This one's comprehensive. The answer is D, all of the above.
All of the above. Okay, that sounds serious. So just to clarify, what makes a variable essential in a welding procedure? Why are they so critical?
Okay, so an essential variable is a parameter listed in the welding procedure specification, the WPS. And it's called essential because if you change it beyond the range that was tested and qualified, it's considered likely to significantly affect the weld's properties, its strength, its toughness, its overall integrity. These are things like heat input, preheat temperature, the type of filler wire or electrode, welding position, stuff like that. They're essential because the WPS is basically proof that welding done under these specific conditions produces a good weld that meets the requirements. Change one of those key conditions outside the tested range, and you've stepped outside what was proven to work.
It really is like a recipe, isn't it?
Yeah.
Change a key ingredient or step, and the result might be totally different.
Yeah.
So let's quickly touch on why all 3 consequences are true. How do mechanical properties change?
Well, changing something like heat input or preheat, as we just talked about with inner pass temp, it changes the cooling rate, changes the whole thermal cycle. That directly affects the microstructure that forms in the weld and the HAZ. Different microstructures mean different properties. Strength, ductility, toughness, they can all change, sometimes dramatically. You might end up with a weld that meets the strength requirement, but is too brittle, for example.
And affecting the quality, that seems almost obvious if you're changing something fundamental.
It is, yeah. Weld quality means it's sound, free from unacceptable defects, fit for purpose. Changing an essential variable could introduce defects, maybe more risk of cracking, porosity, fusion problems, or it could just degrade the overall integrity in ways that aren't immediately obvious as a distinct flaw, but it's just not as good.
And the last one, needing a new procedure approval. That sounds like a major step. Why is that always required?
Because the original WPS qualification is tied specifically to those essential variable ranges that were tested. If you go outside that range, the original test results and approval no longer apply to what you're actually doing. To ensure the weld is still going to be acceptable with the new parameters, you have to write a new WPS reflecting the change, and then you have to qualify it again. That means new test welds, new mechanical tests, new approval. It's absolutely vital for ensuring the weld meets the required codes and standards, and for safety and reliability. No shortcuts there.
A really critical point about procedure control. Okay, last question for this deep dive, focusing on NDT. For gamma radiography of a steel weld at 35 millimeter thickness, the recommended isotope is options: A, thulium-170, B, ytterbium-169, C, iridium-192, D, cobalt-60. Think NDT techniques, which isotope fits this job?
For steel around 35 millimeters thick, the standard recommendation is C, iridium-192.
Iridium-192, okay.
Mhm.
Maybe just a quick refresher, what is gamma radiography used for in welding?
Sure. Gamma radiography is a non-destructive testing method. It uses gamma rays from a radioactive source, an isotope, to see inside a material. It works like an X-ray, basically creating a shadow picture on film or a digital detector. Its main job in weld inspection is finding internal flaws, things hidden inside the weld, like porosity, slag, cracks, lack of fusion, and choosing the right isotope is really key to getting a good image you can actually interpret properly. Different isotopes give off gamma rays with different energy levels, which affects how well they penetrate different materials and thicknesses.
Right, so for this specific case, 35 millimeters of steel, why iridium-192? What makes it the right fit?
Iridium-192, or IR-192, it's kind of the workhorse isotope for a common range of steel thicknesses. Typically from about, say, 10 millimeters up to maybe 60 or 70 millimeter, its energy level gives a good balance. It's strong enough to get through that 35 millimeters of steel effectively, but it's not so powerful that it just blasts through and washes out the detail. You still get good contrast to see potential defects. The other isotopes listed have different niches. Thulium and ytterbium are lower energy. They're better for thinner materials, maybe light alloys where you need high sensitivity for very fine flaws. Cobalt-60 is the opposite, much higher energy. You'd use that for really thick steel sections, maybe 75 millimeter, 100 millimeters or more, where iridium just wouldn't penetrate enough. Using the wrong one, you might miss defects or the image could just be useless. Yeah, absolutely critical to match the tool to the job. Wow, we've actually covered quite a bit of ground there, haven't we? From carbon's role in HAZ hardness to spotting the most serious defects, the impact of interpass temperature, the importance of essential variables, and picking the right radiography source.
We have. And I think the common thread, really, is that this isn't just abstract knowledge for an exam paper. Every one of these points ties back to fundamental principles that dictate how safe and reliable a welded structure is going to be. Understanding this stuff deeply is what allows an inspector to make sound judgments out in the field, judgments that ensure quality and safety. So keep digging deeper, keep asking why. That curiosity is what builds real expertise and confidence.
Couldn't agree more. Well, thank you for joining us for this CSWIP 3.1 exam prep deep dive. We really hope this has clarified some things and given you some solid points to think about. Maybe next time you look at a weld or a WPS, you'll see it a little differently. Keep learning, and we'll catch you on the next deep dive.